and review chapter 13 on equilibrium. Let's see, I want to start with number 1. Yes. Which of the following statements about the equilibrium is false? So we have to think about what we mean by equilibrium. We have a balanced equation. We're implying equilibrium when we put a double part derivative there. Though originally in 101, when we first learned how to balance equations, they always had error to the right. And that implied that everything on the left became everything on the right. But that's not the case. Most, if not all, chemical reactions have some return reaction involved. It may not be much, or it could be the other way around. It could be that most of the reactants stay as they are and produce very little product. The point of equilibrium is to quantitatively assess that value. So, which one of these is false? If the system is heated, the right side is favored. Does that seem reasonable? Let's see. What do we need to know if we're going to assess heating? Well, we know we have 1 mole of gas and making 2 moles of gas here. Usually what we're looking for, but as a general rule, when you heat a reaction, you favor, if you have no other information, you favor an increase in reaction rate because that provides energy for activation energy for these two to come together. And if you don't have information on whether the reaction is exothermic or endothermic, then you can't make you have to make an educated guess. So let's hold that one in reserve, right? I mean, we got the answer there, of course, but let's try to move past that and see why it is. This is a heterogeneous equilibrium. Well, let's see. Gas and solid. Yep, that's true. It's heterogeneous. If the pressure on the system is increased by changing the volume, the left side is favored. So if we have this gas and this solid, and it produces this gas. Okay, now what are we talking about? When you change the pressure on a system, the only thing that's involved is gases. So if we start off with 1 mole of gas and you end up with 2 moles of gas, what does Le Chatelier say? If the pressure on the system is increased by changing the volume, we increase the pressure by decreasing the volume, then it's going to drive this reaction back toward fewer moles of gas. That's the response. So that one is also true. Adding more H2 gas increases the equilibrium constant. The answer is in the statement. Equilibrium constant. That value is constant. The only thing that'll change the constant is temperature. So adding more H2 doesn't do anything to the constant. So D is definitely false. How about removing HI as it forces the equilibrium to the right? We remove this, yes, the reaction is going to continue to the right. That's the disturbance, removing this product. Okay, so what are we faced with? We're faced with a possibility of a false answer here versus a definite false answer. So if you're in the middle of an exam, pick the best answer. Okay? That's my advice. Okay, let's see. Number 2. Do I have number 2 marked off? Yeah, number 2. So we've got a system in equilibrium, and the constant is very small. So K, we say, is less than 1, much less than 1. What does that mean? Well, if you have reactants on this side, making products on this side, what does this K mean? Well, in the simplest form here, right? B over A. So when you look at it that way, this being very small means A is extremely large and B is extremely small. So it makes very little product. So which of these is true? It will take a short time to reach equilibrium, or it will take a long time to reach equilibrium. What does equilibrium say about the rate of a reaction? Nothing. We know that there is activity here, but the equilibrium itself, the constant, says nothing about the rate. It just says, this is where we end up. With a small K, we end up with very little B and a whole lot of A still in that system. So A and B have to be false. The equilibrium lies to the left. Is that true? Yes. Because A is very big, B is very small, the equilibrium lies to the left. The equilibrium can't lie to the left and the right at the same time. And since A, B are both false and D can't be true, then C has to be the answer. On this class. Let's see. I want to look at 3. Yeah, let's look at 3. Shouldn't take but just a minute. All right, for this reaction, carbon dioxide plus hydrogen gas yields carbon monoxide plus water. Okay, what do we have here? We've got all gases. This is a homogeneous equilibrium system. K equals 1.6. Right, so what does that mean? That means the equilibrium is slightly to the right. It's just a little past 1. So our value is going to be in favor of products, but not overly so. At this temperature, 1260 K, that's pretty high. Right? That's about 1,000 degrees, almost 1,000 degrees Celsius. You have 0.15 mole each of CO2, H2CO, and H2O were placed in a 1 liter thermally insulated vessel that was also at 1260. Then, as the system came to equilibrium, all this information is valid, but you don't need it to answer the question. All you need to answer this question is, if it's talking about temperature, it's discussing temperature, then there's your focus right there. What does that mean? That means for this reaction, delta H is a reactant. Because it's endothermic, a positive value of enthalpy. Right? Once you know that, then answering these questions should be simple. The temperature would decrease and the mass of CO2 would increase. Well, if it's endothermic, the temperature would decrease for that reaction. If it's thermally insulated vessel, right, then we can't maintain the temperature. We can't hold the temperature constant. Whatever happens in the vessel stays in the vessel. And remember, in our calorimetry discussions, this is an isolated system in an insulated vessel. That means anything that happens in that vessel stays in that vessel. So the temperature could increase, it could decrease, it could remain the same, it could remain constant. But it's not likely to remain constant. Why? because of this value. Right? That means it takes energy for this reaction to go to the right. That means the temperature is going to decrease. So now we have the possibilities to select out C, D, and E. The temperature will not increase and the temperature will not remain constant. So it's either A or B. So if the temperature is going to decrease, then what happens to the mass of CO2? The mass of CO2 should also decrease. Okay, so B is the answer. Any problems with that? Or is it just putting you to sleep?
It's the white noise.
Yeah,
So I'm fidgeting.
okay. What if you sat away from it?
I don't think it really matters.
Oh, okay. Then you might not be able to see the board too well.
What?
I can go to else, so.
Okay. I guess that's the nature of white noise. It permeates the universe. Okay, how about 4, 5, and 6? Let's see, let me scroll down. 4, 5, and 6 are all about the same reaction. Here we go. Let's go as far as we can up here. Yep, we got it all. Okay. So given this equation, I'm gonna write that. 2A gas yields 2B gas plus C gas. And this is 4, 5, and 6. Addition of chemical B to an equilibrium mixture of the above with what? Well, let's see. If we add, first of all, at a particular temperature, K is very large. K is equal to 1.6 times 10 to the 4th. That means it's virtually all product with very little reactant left over. Addition of B. If we add B, what's going to happen? That way, correct? So let's see, it causes A to increase. Yes, it'll do that. It won't cause C to increase. It will have an effect. Yes, it can be determined. Or none of the above. All right. So this one has to be A or 4. Okay, how about B? At a higher temperature, K is equal to 1.8 times 10 to the minus 5th. K is 1.8 times 10 to the minus 5th for higher temperature. Okay, we increase the temperature. What does that do? It shifts the equilibrium now to the left. So what does that say about this reaction? Because the reaction is either exothermic or endothermic, or some are so close to the middle, it doesn't matter. So if we increase the temperature, how is that shifting this equilibrium? Increasing the temperature shifts it back this way, which means the temperature, the enthalpy is a product. If we increase the temperature, that shifts the equilibrium constant in favor of reactants. So this information tells us that the reaction is exothermic. Okay, now that we know that, if we lower the temperature, it will drive the reaction back to the right. Right? Increasing the temperature may go to the left, decreasing the temperature will go to the right. So it'll cause A to increase? No. Cause B to increase? Yes. And that's why. Because the reaction is exothermic. And we got that information from a change in this constant. Remember, that's the one thing that will change the equilibrium constant for a reaction is changing temperature. And it does that because it shifts that equilibrium based on where the enthalpy is located. Okay, so that was B. That's 6. Raising the pressure by lowering the volume of the container. So now we're back to the original. Raise the pressure by lowering the volume. If we raise the pressure, how many moles? We got 2 moles on this side, and we got 3 moles on that side. So if we increase the pressure, the shift is going to be toward fewer moles, because that will reduce the pressure impact somewhat by reducing the number of moles. I mean, it's Boyle's law. So which one of these satisfies? It's going to move this way. So A increases, B doesn't increase, A increases. And it's solely because we have gases involved. Okay? So that means this one's also A. All righty. Let's see. Let's skip down to number 8. Yeah, everything's on there, so that's good enough. We'll leave it right there. Washed out. You guys are not going to be able to see that. I should have noticed that before. Let me go back to this control. Contrast. That's a little better. Yeah. Okay. How about brightness? Here we go. All right. Well, the first few problems are going to be kind of washed out. So if you watch the video, be sure and have your review document with you so you can follow along until I fix the video. Okay. This question refers to this particular reaction. Okay, plus chlorides yields cobalt. Chloride and 6 water. I don't feel bad, you're interrupting my class. Okay, so what kind of reaction is this? We haven't been introduced to this yet. I don't think. We'll get to that later. This is a complex ion, where this cobalt is surrounded by 6 waters, and it still has a charge. But if we add chloride to the system, then it will displace those waters. And now we have a complex ion with chlorides instead. And the waters are free. The interesting part about this is the difference in color. This one is pink, and this one is blue. So we can qualitatively follow the reaction based upon color change. When cobalt 2 chloride is added to pure water, the cobalt 2 plus ion, when cobalt 2 chloride is added to pure water, the cobalt 2 ions hydrate. Okay. 2 plus ions hydrate. So cobalt is still 2 plus on both sides. And you look at this, 4 negatives are now combined with a 2 plus, which means 2 negatives left over. So that makes sense. And water has no charge, so the 2 plus is attributed to cobalt. You know where we see this reaction? I think. I think we see that in the desiccant that we use, the dryerite. The dryerite is blue when it has no water attached to it. And then when the dryerite absorbs water from its environment, it displaces the chloride and turns pink. And that means the dryerite is expended. It needs to be recharged, heated up. Okay, get back to the question. The hydrated form then reacts with chloride ions to set up the equilibrium shown here. So now we eventually produce this equilibrium by these steps. Now what about it? Which statement below describes the change that the system will undergo if hydrochloric acid is added? So where does hydrochloric acid enter this equilibrium? It enters here. Okay? That's hydrochloric acid because in water, it completely dissociates. Hydrochloric acid is a strong acid, which means it makes hydrogen ions and chloride ions and nothing else in aqueous solution. So now we're introducing chlorides to this side, which should do what? Should drive the reaction that way, to the right. So it should become more blue. Yes, indeed. Can be blue and pink. So B is out. How about the equilibrium will shift to the right? Well, that's true also. A and C are true. Equilibrium shift to the left? No, it can't do both. So two of these are true. C is true and A is true. That's why E is the answer. Now let's see, do we have another one? I'm going to look ahead a little bit, see if we're going to use that one again. Yeah, there's another one, but I don't have it marked. So, all right, so I can erase that one. We'll go to number 9. All right, number 9. We're dealing with this system. Gas, and then some unknown gas here is in equilibrium with this one, 2H2X gas plus energy. So what they're telling us is, not only is this reaction homogeneous, all gases, but it's also exothermic. Now, addition of X2 to a system described by the above equilibrium. So we're going to add this one. What happens? Well, it will cause H2 to decrease. Yeah. Right? You add extra of this, it's going to react with that, make product. It won't cause X2 to decrease. Why? Well, it's going to use up some X2, but we added some more. So X2 is actually going to increase slightly and consume some of this. Right? So X2 will not decrease. And then notice the square brackets. The equilibrium concentration of H2, X2, H2X will increase, not decrease. It'll definitely have an effect. Cannot possibly be carried out. I think I was searching for a fifth one, and that was the best I could come up with. So the answer to this one is A. Let's see. Oh, let's do 10 while we're here. Based on the same equation. Addition of argon to the above equilibrium. Okay. Everything's in equilibrium. Gas, 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 energy. We're going to add argon to that system. What's going to happen to it? It'll increase the pressure, right? But does it have any effect on these guys here? No, it's an inert gas that has nothing to do with this reaction. It increases the pressure, yeah, but just increasing the pressure is not enough to shift an equilibrium. You have to increase the pressure with one or more of the reactants products. So they will have no effect. All right. So that was actually 10. I didn't write it up there. Too late now. Let's see. Need to scroll a little bit. Okay, 11. Which of the following statements is true? We haven't done any calculations yet, have we? Are we going to do something? Yeah. Let's see, how much time do we have? 8:30. Oh, all right, we got time. So we're looking at number 11. Which of the following statements is true? When two opposing processes are proceeding at identical rates, the system is at equilibrium. But that's a good definition of equilibrium. Opposing processes. You can say that about anything. It doesn't have to be chemical equilibrium. You can say this: opposing processes are proceeding at identical rates. That is a state of equilibrium. It just turns out that in this class, we're talking about those opposing rates being forward reaction versus reverse reaction. How about catalysts are an effective means of changing the position of an equilibrium? Do catalysts do that? What does a catalyst do? Well, at the atomic level, it offers an alternative route for the reaction to proceed. Which means I can't imagine a catalyst that would make a reaction go slower. It actually speeds up the reaction by offering that alternate route. And that alternate route decreases the activation energy of the reaction. So catalysts have an effect on the kinetics of the reaction, but not on the equilibrium, because a catalyst will cause an equilibrium to shift forward and backwards equally. The concentration of the products equals that of the reactants and is constant at equilibrium. Well, no. We know that the equilibrium constant can be very large or very small, which means you can have an imbalance of reactants and products. They're not equal. Endothermic reaction shifts toward reactants when heat is added to the reaction. An endothermic reaction. That's an endothermic reaction. Enthalpy is over here. Shifts toward reactants when heat is added. It shifts toward products. Okay, so that was false. The only one that's true is A. How about 12? Let's see, I've got a mark here. Why did I do that? Let me look at the video. That's the key. Let me look at this one. See if there's a change. And okay, I got it. All right. Let's dig into it and see if I can determine why I made that mark. Well, so we're considering this reaction. Oh, obviously, just dawned on me. There needs to be a plus sign right there. So A is a gas, B is a gas, in equilibrium with what? C is a gas, and D is a gas. Okay. Upon adding gas A, the value of K does what? Oh, this is too easy. When you add reactants or products to this or subtract reactants or products, what does it do to the K? Nothing. We didn't change the temperature, we only changed the. It does cause the position of the reaction to change, but not the K. So the value of K does not change as long as the temperature is constant. All right. So let's see, did I fix that? Yeah, I fixed that in your document. I just didn't fix it in the key. Okay, let's go down to 17. Okay. Oops. There we go. That's everything. Ammonia is prepared industrial by this reaction. Remember what that reaction is called? Called the Haber process. Well, actually, Bosch got involved too. He improved on it. But Haber got it started. Fritz Haber. And the delta H for this reaction is negative 92.2 kilojoules at 25 degrees. Well, that's what the zero means. That's standard temperature, standard conditions of 25 degrees. And that K then is equal to 4.0 times 10 to the 8th. So the equilibrium position, the equilibrium constant says that it favors that product. Right there. But how about the reaction rate? Doesn't say anything about the reaction rate. So even though the equilibrium favors this product, how fast does it occur? Well, Haber discovered that it didn't occur very fast. So on an industrial scale, that doesn't do you any good. It doesn't matter if the product is favored if you can't make much of it. So he said, all right, I'm going to speed the reaction up by increasing the energy for activation, right? Make a higher temperature. But what happens then? Well, with a negative delta H, you're forcing the reaction back to reactants, not products. So he increased the rate. Well, he increased the activation energy, but he decreased the amount of product produced. So what was his solution? Catalyst. Increase the temperature, introduce a catalyst. So he searched around for a catalyst. Turns out a very effective catalyst for this reaction is finely divided iron, pure iron. And that reaction will go fast enough so that you can produce some product. That's not the only thing he did. As he was producing this product, in this reaction, he drove the reaction to the right based on the Chatelier's principle by removing ammonia as it's formed. So in the reaction vessel, you've got all this going on, and he's recirculating. He's taking part of the reaction products out and cooling them. Ammonia drops out first. These guys stay gases because they have a very, very, very low boiling point. So he removed ammonia, and then he shunted those gases back in to the reaction vessel. And by doing that, he drove the reaction to the right. Okay, enough history lesson. When the temperature of the reaction is increased to 500 degrees, so we're going from here to 500. which is what Haber did. Which of the following is true? K for the reaction will be larger at 500 than at 25. No, we increase the temperature. That means we drive toward the reactants and decreases the K. Because you're producing more product, more reactant and less product. So that means this drives the K to a smaller value. So this means smaller K, simply because of that condition. It's exothermic. All right, so A is not it. At equilibrium, more ammonia is present at 500 than at 25. No. If this is a product, it's over here. Then when you increase the temperature, you drive back toward reactants. So B is false. Product formation at equilibrium is not favored as the temperature is raised. That is true. Because this is considered part of the product, Le Chatelier's principle. Then if you increase the temperature, you drive the reaction back this way, product formation is not favored. Okay. The reaction of N2 and H2 to form ammonia is endothermic. Well, no, that's false. That's a negative value. It's exothermic. So the only one that's true is C. Okay. That's 17 plus a history lesson. I often wonder what the scientists' thought processes are when they're working on these things. Because this is original material. Nobody told him. He just deduced from what he knew what had to happen. Because the necessity is the mother of invention. Germany needed this product desperately. Because World War I, they couldn't get hold of nitrates to make their explosives and propellants for their ammunition. So Haber's work and Bosch also work on this process allowed Germany to continue the fight by making their own nitrates eventually. You make ammonia first and then you convert it to nitrate. That's the hard part. Okay. Legumes do it just as a matter of course. Like clover. Trying to think of some other soybeans. That's a legume. They take nitrogen from the air and they fix it into ammonia in their roots. They have little nodules on their roots. If you pull one up and cut the nodule, if it's pink, then it's active. It's got little bacteria down there that are taking this nitrogen from the air and fixing it as ammonia. And the plant and the bacteria can both use that nitrogen. Nitrogen in the air is not useful. Plants can't use it. It needs to be fixed. That's called nitrogen fixation. But they do it using biological catalysts, enzymes. Okay, let's see, how about 20? There we go, 20. The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. So we got this stuff, 2HGO, solid, is in equilibrium with liquid mercury and oxygen. And the delta H is 43.4. That's a positive. So that means 43.4 kilocalories per mole. Okay, or mole is on this side of the reaction. It's endothermic. The mass of HGO in the bulb could be increased by what? So the problem is we want to make this one go up. We want to increase that. So what will do that? Well, let's see what our choices are. Removing some mercury. If we remove the mercury, it's going to go what? That way. So that won't increase this. Reducing the volume of the bulb. Well, let's see. Where are the gases? We've only got one gas. So if you reduce the volume, we go from 1 mole of gas to 0 moles of gas. That is a valid response. You're decreasing the moles of gas in response to an increase in pressure. So yes, B will work. How about adding more Hg? The mass of Hg in the bulb could be increased by, well, if you add more of this, well, add more mercury does what? Does it increase the concentration of mercury? That's the question. Look at the equilibrium expression here, K. What can we put in K? Can't put the solid, can't put the liquid. K is only responsive to O2. Okay? That's why adding more mercury will have no effect on this reaction because it's not part of the equilibrium expression. You don't change the concentration of mercury by adding some. Now, what could it do? If you add mercury and the volume is constant, then you're taking up volume of liquid and you're decreasing volume for the gas. So decreasing the volume for the gas could theoretically push the equilibrium back that way. Right? So if you made that argument, then I'd have to concede. Unless there's something in here that says, glass bulb, you have to assume that the glass bulb can't be. I mean, that's why we say it's a glass bulb. How are you going to change the volume of a glass bulb? Well, no, that would lend itself to this argument, adding more mercury. Add more mercury, then you decrease the volume available for the gas, which does shift that to the left. So actually, B and C with that argument would work. Increasing the temperature, now it's endothermic, drives it to the right. Removing some oxygen, now that moves it to the right. Okay, so this says you can reduce the volume of the bulb. All right, so if we can reduce the volume of the bulb, we can increase the volume of the bulb to compensate for adding mercury. So in this case, choose the best answer. And the best answer is B. All right, that was 20. Let's see. 21. All right. At 500 K, 1 mole of gaseous ONCl. ONCl. Okay, is placed in 1 liter container. So the volume equals 1 liter. Temperature is 500 K. 5.3% dissociated, according to this equation. So it's going to go this way, 2NO plus Cl2. And all of these are gases. All right. Determine the equilibrium constant. Did they say that? This should be marked as a gas, and that's the gas. Nitrogen monoxide is definitely a gas. Chlorine's a gas. That's a gas. So we have to assume that, or we're kind of dead in the water. So what's our K expression? Right. NO squared Cl2 to the first power and ONCl to the first power. Oh, second power. Okay, so there's our equilibrium expression. What's the constant? Well, what are we getting? 5.3% dissociated. 5.3% dissociated at equilibrium. All right. So let's see, I should have put this, let me put it back up here. 1 liter and temperature equals 500. Okay, because I'm going to need this space. In fact, I should have written this one someplace else too. Why do I need that space then? One word. Ice. We need an ice table. If we're gonna plug in values here, we need to know what those values are in order to calculate the equilibrium constant. And the only relationship, the only indication for concentration that we have is 5.3% dissociated. So, initial change equilibrium. Be sure I'm on the right track here. Yep. Okay, 21. What else were we given? Oh, I missed that part. 1 mole of this compound per liter. So its concentration is what? 1 molar. Yeah, I need a new marker to have it. I got a blue one. Let's see if it works. Purple. Okay. If this is 5, yeah, I did that. There we go. If this is 5.3% dissociated, we start off with 0 here and 0 there. We didn't put any of that in there. So the change is we're going to lose 5.3% of this one. Right? So 5.3% of 1 is what? 1 minus 0.053. Actually, that's not right. The change is we're going to lose 0.053. Is that 5% times 100? 1, 2. Yeah, 5.3%. So we lost that much. So what did we gain over here? Well, we gained the same amount of NO because they're 2 to 2, 1 to 1. So actually, 0.053 here. How much of this did we gain? Well, only half of that. Right? 0.0215, correct? That makes 3 here. No, that's not right. 2 that's 2. 213 is 6, 5. There we go. Okay. So now we have what here? Well, let's see. We have 9.375 minus 4. 9.947, correct? Subtracting from 1. Yep. And then 0.053 and 0.0265. So there are our values. And all we have to do now to calculate K is to plug in the numbers and don't forget your powers. So NO is 0.053 squared And chlorine is 0.0265. And 9.947 also squared. Okay, so let's see if I can get the same value as in the key. 0.053, and let's square that. And then 0.0265 times that value. And then 9.947, and square that first, and then divide it into that form of compound. So I get 7.6. Having significant figures. 2, I can have 2. 7.5 times 10 to the minus 7. Okay, is that one of them? No, it's not. What did I do wrong? Hold on a second. I missed something. 1 mole in 1 liter. There. 5.3% dissociate. 5.3, so we're going to lose that much. We're going to gain that much there, that much there. See where my mistake was. Oh, here it is. I calculated that one wrong. Let's do it using the calculator. 0.053. Yeah. Added an extra 9 in there. As usual, my students didn't catch it. There we go. So if we change that one to 9.47, then we should get 8.3. Okay. The process is correct. The math was wrong. All right, let's see. 22. Up on the board. The purple leaves a shadow. The reaction below, calcium carbonate, it's a solid, and it decomposes to calcium oxide, also a solid, plus CO2. Okay. So what's the equilibrium expression for this? I'm going to write it over here. K is equal to CO2. That's it. Because that's a solid and that's a solid. So what's the Kp value equal to? Okay, let's put that subscript in here. Because this is based upon pressure. And that value is 1.16 at 800 degrees. Okay, that's given. All that stuff is given. If 31.3 gram sample of calcium carbonate, 31.3 gram sample, was put into a 10 liter container. The volume equals 10 liters. And heated to 800 degrees. What percent of calcium carbonate will react to reach equilibrium? All right. We know that the equilibrium is based only on the amount of carbon dioxide produced. And it's this value. And that's related to pressure. And we can only assume that the pressure here is in atmospheres. Right, so how do we approach this problem? Well, we know the volume. We know that this equilibrium value is going to be related to how much carbon dioxide is produced. So at equilibrium, the amount of carbon dioxide is equal to that value. 1.16 atmospheres, isn't it? Yeah, I think so. So that's where we start. So at equilibrium, carbon dioxide pressure is 1.16 atmospheres. What do we know? Well, we know pressure. Okay. We know pressure. We know temperature. Okay. We know volume. Right? What do we need to know? We need to know moles. Right? Because with this balanced equation, we can't do anything unless we know moles. So how many moles of carbon dioxide is represented by that pressure at this temperature and that volume? Remember the equation? Ideal gas equation. So solve for M. And we have EV over RT. So what's the pressure? 1.16 atmospheres. The volume is 10 liters. R is what? 0.08206 liter atmospheres per mole. Okay. And then temperature is 800 plus 273. Has to be in K. Never thought you'd see that equation again, did you? That's the reason this problem is there. Okay, so how many moles of carbon dioxide do we have? Let's see if I can do this one without making a mistake. 1.16, 10 times that, 0.08206 divided, and then 800, 273 plus that, divide that in. So I get 1.3, I'm going to keep a bunch of decimals for now. 1.317. Actually, that's the moles of CO2. Okay. So how many moles of calcium carbonate does that represent? First of all, how many moles of calcium carbonate did we start off with? Actually, let's go back to the question. What percent of calcium carbonate will react? Percent, that's mass. Okay. So we keep that mass and we find out using this, what mass of that was decomposed. So this is related to calcium carbonate 1:1, is it not? So it's actually 1.317 moles of calcium carbonate. So it's one of each of these. Is that right? One carbon, 2, 3 oxygens, 1 calcium. Okay, it's balanced. So that many moles of calcium carbonate is equal to how many grams? What's the molar mass of calcium carbonate? Well, we have to add it up. Calcium is what? 40.08. Carbon is 12.01. Oxygen, 3 times 16 is what? 48. So 100.09. Oops. Right. There we go. 100.09 times that value is 13.2 grams of calcium carbonate decomposed. So the percent, to answer the question, what percent of calcium carbonate was reactive? How much of it was decomposed by percentage? 13.2 divided by 31.3. And I get 42% or 42.1%. B. Okay. I know we had to dance around the barn several times to get there. It took me a second to actually wrap my brain around this problem.
On ours, it says 42.4.
Really?
Yeah.
Okay, that's okay. Depends on how you round. That's a rounding error. So in that case, pick the best answer. Or, let me see, why would it say that? What if we round this? We can only keep, let's see, 1.16 atmospheres. We can keep 3 here. So 0.132. 0.132 would be a rounded. Would be rounding times 100.09. That will give me 13.2. What's it say? Should be 42.1. Let me look at my copy. Number 21.
22.
22, excuse me. Yeah. Huh. It should be 42.1. Check one other thing here. Look at the work problems. Okay. I see. Use four significant figures were kept. And this was converted to moles, into the ratio of moles. Actually, the mass ratio is the accurate one. Based on the question. What percent of calcium carbonate, it has to be based upon this because that's what was given, will react. Okay, so it should be 42.1. Let's see. All right. 22. Okay, we're good. Next one on my list, let's skip to 24. There we go. 24. Nitrogen gas reacts with hydrogen gas to form ammonia. Okay. Then give us the equation. That's the Haber equation, obviously. At 200 degrees in a closed container, 1 atmosphere of nitrogen gas is mixed with 2 atmospheres of hydrogen gas. At equilibrium, the total pressure is 2.2 atmospheres. Calculate the partial pressure of hydrogen. That's because we don't need the balanced equation to do this one. This one is based upon Dalton's law. I'm pretty sure. Let's see, what are we given? Nitrogen gas and hydrogen gas react to produce ammonia. All right? At 200 degrees. So maybe it's Dalton's, maybe it's not. 200 degrees Celsius. All right. 1 atmosphere of nitrogen gas, 1 atmosphere, is mixed with 2 atmospheres of hydrogen gas. At equilibrium, the total pressure is 2.2 atmospheres. So this is initial, and this is total pressure is 2.2 atmospheres at equilibrium. So at equilibrium, the pressure is 2.2 atmospheres. What's the partial pressure of hydrogen gas? All right, as a matter of fact, we do need the balanced equation. Okay, so if this one shows up on an exam and you're not given the reaction equation, then ask for it. I'll give it to you. So we have nitrogen gas, hydrogen gas, yields ammonia. Okay, balance this equation. 2 there, 3 there. 6, 2, 2. There we go. Okay, so we're going to need, in order to determine the partial pressure of hydrogen gas, we need we don't have the K. How are we going to do that without the K? Oh. Okay. We don't need K. I'll show you why. Initial change equilibrium. All right. The initial pressure for nitrogen is 1 atmosphere. The initial pressure for hydrogen is 2 atmospheres. The initial pressure for ammonia is 0. So what's going to happen? Which way is the reaction going to go? To the right, right? So we're going to lose some nitrogen. How much hydrogen are we going to lose? We're going to lose 3 times that much. How much ammonia we're going to get? We're actually going to get 2 times x because it's 2 to 1. Okay, so the equilibrium situation is 1 minus x, and this one is 2 minus 3x, and this one is 2x. So the final pressure was given as 2.2 atmospheres. Okay. This is the partial pressure of hydrogen gas right here. 2 minus 3x. We need to find out what portion of this is. This is the total. So this is going to be equal to that, plus that, plus that. Okay. Yeah. These are partial pressures of the gases at equilibrium. So this is equal to 1 minus x for nitrogen plus 2 minus 3x for hydrogen plus 2x for ammonia. And we want to find out what this one is. Okay. So what do we have here? We've got an equation in one unknown. So actually, it would have been more efficient to make this one x. Then once we answer the x question, we got our answer. Well, neither here nor there. We just need, once we find x, we plug it in that formula, and that's the partial pressure of hydrogen. So let's solve for x. Okay. Minus, plus, okay, these are all pluses or minuses. So we can say 1 plus 2 is 3. Okay. And 2x minus 3x is a minus x, and a minus x is minus 2x. Correct? Or minus x minus 4x, 2x minus 2x is equal to 2. So now we have, let's put 2x on this side, makes it positive, and 2 minus 2.2 here is, let's see, 0.8. Okay, so x is equal to 0.4. Now this one is equal to 2 minus 3 times 0.4 is equal to what? 3 times that is 1.2. 1.2, right? 3 times 0.4. Yeah. Sometimes I get in trouble trying to do these in my head. 1.2 from 2 should be 0.8, right?
You say 0.8?
Yeah, 0.8. 1.2, 2 minus 1.2. So 0.8 plus that would be 2, correct? Two minus 1.2?
Yeah.
Okay. So there's our partial pressure of hydrogen. Right here. So as it turns out, we used our ice table, and to answer the question, we didn't need to know what K was. Could we calculate K? Sure. We know what X is. Put X in here, 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 and well, actually, yeah, we've got 3 gases. Then put it in your equilibrium expression. You can find out what K is under those conditions. But we didn't need to do that, not to answer the question. Okay, that was 24. I didn't need Dalton after all. How about 25? So Oops, scroll just a hair. Okay, we are going to calculate K for this one. And we're going to use that same equation. Just put them in different order. Two moments. Okay. Yep. Okay. The equilibrium concentration of ammonia is 0.55 moles per liter. What's the value of K? The formation of ammonia. Right. So if we build our ice table, it tells us the equilibrium concentration of ammonia is 0.55 moles per liter. 0.55 molar. Okay. How did it get there? Well, if we start off with 2 moles of N2, and this is in a 1 liter container. Okay, so we're starting off with 2 molar N2 and 4 moles of hydrogen per liter. So that's 4 molar. There we go, starting conditions. And that's 0. So how did we get here? That was the change. Okay? That was the change. So how much is this one? One of these gives you 2 of those. So that means half of that is this value. Okay. I'm going to use my calculator. Last time I did this in my head, I got in big trouble. 0.275. 0.275 minus. That's what it took to make this. 1 of those makes 2 of these. 3 of these makes 2 of those. Or it's more convenient, actually. 1 of these requires 3 of those. So 3 times that would be this value. 825 minus 0.825. The ratio is 1 to 3. 1 to 3. This amount had to react to make that amount. Okay, so now we've got, oops, we need this again. 4, 3.175, 175 molar equilibrium, and this is 0.275 to 1.725. So there we have our equilibrium concentrations. We can calculate K. So what is K? Ammonia squared divided by hydrogen cubed, also divided by nitrogen to the first power. So we just plug in our values. Ammonia, 0.55 squared. Hydrogen, 3.175 cubed, and nitrogen, 1.725. There we go. So 0.55 squared is that key, and 3.175 cubed divided into that value, and then 1.725 also divided. So I can get 5.2 significant figures. 5.5 times 10 to the minus 3. There it is. That sort of confirms what I was saying earlier, right? We have that huge, that large value greater than 1 at a given temperature. But when you increase the temperature, you drive the reaction backwards and you make a smaller K value. So when we heat this thing up to, what is it, 700 degrees Celsius, we change the equilibrium constant to favor reactants. All right. $25. Let's see, what do I have next? 26. Okay. All right. Now we got a real test of our memory. Given the equilibrium constants for the following reactions, what's the K for the system? This one. So what you're going to do is you're going to use Hess's law. You're going to combine these two to give you this equation and then calculate the K in terms of these Ks. That's the whole point of this exercise. So if we're starting off with 4 coppers plus oxygen yields CU2O, correct, solid. And this is a K1. I want to drop down here in case that we need to modify that. Put this one in. 2 CuO yields CU2O plus 1/2 B2. And our target reaction is 2 coppers plus oxygen yields 2 CuO solid. We want to know what the K is for this one. Okay. So what do we do first? Well, I would look at reactants and products here and see where they're located in these two. Copper, it's right here. So that one's good on this side. Right, we're good there. How about oxygen? Where's oxygen? Oxygen's here, plus it's over there. Right, so we can't say anything definitive yet. How about CuO? CuO is here. Needs to be on that side. So we're going to have to flip this one in order to get this on that side. Right, so let's do that first. So now we're going to have CU2O plus 1/2 O2 yields 2 CuO solid. So now we got this one on that side. What does that do to the K? When you invert the reaction, it inverts the K, right? Because now reactants are products and products are reactants. So it flips the K on its head. So that means now the K is going to be the original K to the -1. It's the inverse of the K from this equation. Okay. So now that we got the 2 CuOs here, let's look at this one. Everything's on the correct side of the arrow, but it's the wrong number of things. We need 2 coppers, not 4 coppers. So what do? We divide by 2. So 2 Cu plus 1/2 O2 yields 1/2 Cu2O. Okay, what does that do to the K? When you multiply by a value, that becomes the power of the K for the new equation. So this would be K1 to the 1/2 power, or the square root of K2. K1, excuse me. Okay, now if we use this equation and this equation, is it going to give us this equation? Right. There's two columns. There's oxygen. There's a half an oxygen here and a half an oxygen there. Okay. There's C2O. Did I write those correctly? Okay. Cu2O, which is not in that equation. So I did something wrong. Oh,
There's a half one there.
right. That should be a 2, which means that's a 1. I see my mistake. Okay. So now this one cancels out. We're using this equation and that equation. And we got to account for CuO. There are 2 CuOs here and none there. Right? That's it. Okay. So we've got the K for this equation and the K for this equation that have to be combined. So when you have K's for 2 equations, you add the equations together. What happens to the K's? You multiply the K's. So this K is going to be equal to this one times that one. Okay. So let's look what our choices are. I need to scroll on. What are our choices? Well, it looks like we don't have any negative powers here, so we need to put that one into its equivalent position, which would be in the denominator, correct? Because this is 1 over K2. 1 over K2 times K1 is equal to, this one's still on top, 1/2, and this one now comes down to the bottom. Right? That's in the denominator. It's in the denominator here. So which one matches? K1.5, yeah, E. All right. Think you can do that one on your own? You can't circular nod. All right. This is an exercise in, everybody knows Hess's law from first semester. This is an exercise in what do you do with equilibrium constants when you use Hess's law. All right, how about 28? There we go. Exactly 1 mole of N2O4 is placed in an empty 1 liter container and is allowed to reach equilibrium, described by this equation. N2O4 decomposes into 2 NO2s. Now let's put that equation up there. N2O4 gas decomposes to 2 NO2s. Okay. We're given the equilibrium condition is N2O4 is 37% dissociative. what's the value of the equilibrium constant, Kc? Kc means molarity for the reaction under these conditions. All right, so we have two gases. That means both of them enter into the K value. So what are our initial conditions? Well, N2O4 is 1 mole per liter, is 1 molar. And this one is 0. So what's the change? Well, 37% of N2O4 is dissociated. So what's 37% of this? 0.37 molar. That's how much is dissociated. So what is produced over here? Plus 0.74 molar. So this one's going to be 0.74 molar. And this one's going to be, let's see if I can do this one here. 3.9. Yeah, I think that's right. Now let's go back to the question. What's the value of the equilibrium constant? Okay, so the equilibrium constant is equal to what? It's NO2 squared into O4. The first power. So we plug in this value, 0.74 squared, and this value, 0.63, and see if I get the answer that's in the key. 0.74 squared, 0.63, and let's see, two significant figures. 8.7 times 10 to the minus 1. All right, or 0.87. Same thing. Okay, that was 28. Let's see. Do we need to do 29? Consider the reaction. Hydrogen gas, iodine, makes 2HI, for which K is 44.8 at a high temperature. So I'll bet you $1, since this is way to the right, that this reaction is endothermic. You increase the temperature very high, and you get a huge K, then yeah, it's probably endothermic, which we may not need to know for the solution. If an equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, determine the equilibrium concentration of hydrogen. All right. And we have H2 plus I2 yields 2H5. Now, are they saying that they don't tell us that we know hydrogen is a gas? Do we have to assume that the others are also a gas? They must be. Because it says high temperature. Yeah. So these are all gases. All right. So it looks to me like in order to find the concentration of one of them, we're going to need to know, we have the K, we're going to need to know, set up an ice table. All right. Equimolar mixtures of reactants give the concentration of the product. So equimolars of this means that's 0. The concentration of the product is 0.5 molar at equilibrium. That means we had to get this much from the reaction. Right, the change had to be a positive 0.5 here, which means this is 2 to 1, so this had to be 0.25, 0.25 subtracted. So when it says equimolar, that's what's got me puzzled. All right, I'm going to say this. If we started out with a certain amount here, equal amounts, and we subtract like that, then will that get us to the answer? What's the equilibrium concentration of hydrogen? Yeah, probably will. But look, these are equal to one another, aren't they? Right? Why don't we just say this? That's equal to y and that's equal to y. That could simplify things because this y will give us the equilibrium concentration of hydrogen. So our value for K is 44.8. 44.8 equals K, and K is equal to HI squared divided by H2 to the first power times I2. Right. So this one is going to be 0.5 squared. And this one's going to be y squared, right? Y times y. Yeah, we can do that. So let's take the square root of this whole equation. Can we do that? Square root of this one, square root of that one. Right, so what's the square root of 44.8? 6.693. 6.693 equals, what's the square root of this one? Well, it gets rid of that square, that square. So it's 0.5 divided by y. So y is actually 0.5 divided by 6.693. And I get 7.5 times 10 to the minus 2. 7.5 times 10 to the minus 2 molar. There it is right there. Okay, did I lose anybody? Are we good? We could have gone ahead and solved for x, right? Just gone ahead and muscled through it. And then we would have gone back and plugged it into this equation to find out what hydrogen is. But if these are both equal, why not just call them y? Because that gives us the answer. That was my shortcut. Okay, that was 29. Let's see. We're good on time. Yeah, we're good. All we have to do is stay awake, right? And watch the allergies. Okay, 30. You can scroll down. Okay, 30. Consider this reaction. 2HF yields H2. 2HF yields H2 plus F2. Is that right? Yeah, that's balanced. And the K is 1 times 10 to the minus 2. Okay. Given 1 mole of HF 0.362 moles of H2 and 0.5 moles of F2 mixed in a 5-liter flask. What's the reaction quotient? So we have 1 mole per 5 liters for this one, initial. So that's 1 per 5. And this one we have 0.362 per 5. 362 per 5. And this one we have 0.750 per 5. So what's the Q? How do we calculate Q? Do we need to know the equilibrium concentration? No, that's the whole point of Q. Calculate Q and compare it to K to see which direction the reaction is going to go. That's not the question here. They just want to know what Q is. Right? So we just need the expression for Q will be the same as the equilibrium, only not square brackets. So we would say H2 times F2 divided by HF squared. So we just say H2 is 0.362 divided by 5 times 0.750 divided by 5. You wonder why I'm leaving the 5s here? And then 1 divided by 5 squared. Okay? So what does that give us here? That gives us this times this divided by 5. Actually, 5 squared. That times that, that times that. So I've got 0.362 times 0.750, and that's divided by 5 squared. And this is 1 divided by 5 squared. Squared 1, squared 5, 5 times 5, 5 squared. Squares go out, and we have this times that. 0.362 times 0.750. Is 0.272. 0.272 is Q. Right here. All right, just for fun, which way is this reaction going to go? If K is 1 times 10 to the minus 2, which would be 0.01. Q is larger than K, which means what? It means it's got too much product. It's too big here. So if it's got too much product, it's going back toward reactants. You need to know that if any other questions say, right, what's the equilibrium concentration of HF? You need to know which direction the reaction is going in order to do that. But to answer the question, 0.272 is the answer, B. All right, let's see. That was 32. 32. Scroll just there, get back up. There we go. Carbon disulfide and chlorine react according to the following equation. So CS2 carbon disulfide plus chlorine react to give you S2Cl2. Right. These are 2 nonmetals. How do we name that? Well, actually, chlorine and sulfur. Yeah, I guess sulfur would come first. Disulfur dichloride would be the name of that compound. And then carbon tetrachloride is also a gas. Okay, when 2.14 moles of CS2 and 5.85 moles of Cl2 are placed in a 2-liter container and allowed to come to equilibrium. So that's our initial condition. 2.14 moles per what? 2 liters. So that's our molar concentration initially for carbon disulfide. And then 5.85 in the same 2 liters. Allowed to come to equilibrium. So we start off with that much product. Then we have a change, and we have equilibrium. Okay. What other information we get? The mixture is found to contain 0.62 moles of carbon tetrachloride. 0.620 moles per 2 liters. Okay, that's equilibrium for carbon tetrachloride. How many moles of Cl2 are present at equilibrium? So we need to know this concentration and times 2 moles, 2 liters. Once we find this, that's not the answer. All right, how did we get here? Well, we had to add this much. What is that? 0.310 molar. So we had to add 0.310 molar, 1 plus 0.310 molar. We had to lose, these are all 1, right? 1. We had to lose 0.310 and lose 0.310. Okay. So we don't even need to calculate K. Hence, that question refers to this value right here. Right? So 5.85 divided by 2 was the original concentration. 2.925 molar minus 0.310 molar. 2.615 molar, but there are 2 liters, right? Molarity times volume equals moles. So 5.23 moles. Is that right? What did I do wrong? Oh. You guys gotta watch me. So that means 3 to 1 means we have to lose 3 of these. Minus 9, 0.930. So now this one minus that. We can probably do that one close enough in our head to find the answer. Right? That's a little more. It's a little less than 2. So 2 times 2 is 4, so it's less than 4. Right here, 3.99. All right, see how I did that? Let's subtract this from that. Just a hair less than 2 is the answer. 2 times 2 is 4, so it needs to be less than 4. So not much, just a little bit less than 4. So there you go. And that way you can move on to the next question in a minute. Not dilly-dally over details. 33. I think it's 33. Okay. At minus 80K, minus 80C, K for the reaction N2O4 to NO2 is 4.66 times 10 to the minus 8. So it favors reactants, not products. It favors reactants aniline. We introduce 0.047 moles of N2O4 into a 1 liter vessel at that temperature and let the equilibrium be established. The total pressure in the system at equilibrium will be what? Okay. Okay, it says K, and it gives us moles and liters. So I assume this K, since it doesn't have a P subscript, this K is in molarity. N2O4, and I'm not even going to write gas because they're both gases. Okay, we have that. We also have the K. K equals 4.66 times 10 to the minus 8. Okay. Now, initial conditions. 0.047 mole. 0.047 moles per 1 liter. So 0.4 molar. Okay. And allowed to come to equilibrium. It means we're starting with that. Change equilibrium. Okay. The total pressure in the system at equilibrium will be what? All right. So that I don't waste your time dancing around the barn. What's the change? Well, which way is the direction? The reaction will go. To the right, obviously, because there's no product there. So we're going to add, we're going to subtract an X from this side. And then twice that much shows up over here. So this is going to be 2X, and this is going to be 0.047 minus X. So we need our expression here, which is equal to NO2 squared divided by N2O4 equilibrium, which equals what? Well, this is 2X squared, and this is 0.047 minus X. Okay, it's equal to that value. All right. Now here's where we have to say, all right, do we need to simplify this? Right, otherwise we end up with a quadratic. Can we do it without a quadratic? When the K is that small, a simplification is a valid approach. So let's see. What we're saying is this is X. And if the K is very small, how much of that? What size X relative to this value? 10 to the minus 8. This is minus 2, that's minus 8, 6 orders of magnitude smaller. So this X is insignificant. It's so small, it doesn't matter. So we're going to say 4.66 times 10 to the minus 8 is equal to, let's go ahead and square that, 4x squared over 0.047. So let's solve for x. Multiply this times that, divide by that, and take the square root. I found my calculator. Did I tell you I was in Greenbrier the other day teaching 101?
That's all I'm using.
Yeah. Did I leave the part in where I lost my calculator? I cut that out, didn't I?
We looked for that calculator everywhere.
Oh, you were there.
And he put it in his phone.
It was right here instead of my phone. It was right there the whole time.
Because it was funny because I looked and I was like, your phone's on the table. And he was like, let me check my pocket right here. And he put it in his phone pocket.
Comic relief for sure. Okay, so let's do this 4.66 exponent to the minus 8, and then multiply times 0.047, and then divide by 4, and then take the square root. So that's 2.34. 2.34 times 10 to the minus 5. Okay. Okay, so let's go back to the question. The total pressure in the system at equilibrium will be the total pressure. All right, what we have to do is calculate the number of moles of gas. Why do we need that? Well, let's see. We've got temperature. We've got volume here, volume. If we get the moles, then we can calculate the pressure using the ideal gas equation. So if this is molarity of X, 2 times X is 4.68 times 10 to the minus 5 molar. And what's the volume? 1 liter. So 1 liter times that is 4.68 times 10 to the minus 5 moles of NO2. Okay, we've got that one. How many moles is this one? We'll take that X and subtract it from 0.047. Not going to be much. 0.047 is 4.70 times 10 to the minus 2. Yeah, it didn't change it. Like I said earlier, and it has a little effect on this value. So, what are the total moles of gas here? Add those two together. That one. Oh, I did it in my head. That's why it's not here. 4.68 exponent 5 to the negative plus. So I get 4.7023 times 10 to the minus 2. Okay. So if PV equals nRT, we want to find pressure. Pressure equals nRT divided by V. So the number of moles is this total, 4.7023 times 10 to the minus 2. R is 0.08203 liter atmospheres per mole K. Temperature is minus 80 plus 273. And volume is 1 liter, right? Okay. So let's take that 273 and subtract 80 from it. So that's 193. Okay. And times 0.0820, is it 3 or 6? I think it's 6. I put it in useful information. Yeah, 6. Six times that, and then times 4.723 times and divide by 1. So I get 0.7 2 degrees freedom. 4 atmospheres. There it is. Okay. I bet you $1 that if we just use this value right here, since this value is so small, you're not going to have much of that. So if we use 0.047 instead of this one, I bet we'll get the same value, don't you? logic would have it that with an equilibrium constant that small, this contributes nothing. So we could save ourselves a whole lot of time just saying, by saying 0.0470 in this value in here. And do the calculation. All right, that was 33. We got lab to do today. Let me see if I can wrap this up. I'm in order yet. Just a couple. Okay, we're good. Number 34. You can see all up there. A sample of solid what? The bomber's friend, ammonium nitrate. Well, 6%. Ammonium nitrate, 6% fuel oil. With a stick of dynamite will do the job. Was placed in an evacuated container and then heated so that it decomposed explosively according to the following equation. Produced N2O. What's N2O? Ever been to the dentist? Laughing gas, nitrous oxide. That's the N2O. And water. At equilibrium, the total pressure in the container was found to be 2.63 atmospheres. Calculate Kp. All right, let's see if we can do this. So here's ammonium nitrate, which is a solid, right? Has no impact on the equilibrium concentration. And water. That's a gas. Okay, so K is actually going to be nitrous oxide times water. There. Oop. Squared. Okay, so let's see, what do we know? Initial change equilibrium. The total pressure in the container was found to be 2.63 down here. Right. So these two together are 2.63 atmospheres. Right? Okay, so far, 2.63 atmospheres. All right, what does this ratio here mean? That's a mole ratio, which is proportional to pressure. So the partial pressure of nitrous oxide is half that of water. In other words, 1/3 of it is here, 2.63. Divided by 3 is 0.877, 0.877 atmospheres. What's left over? .75 atmospheres. Let's see, does that add up? There you go. Does everybody see how I got that? Dalton's law of partial pressures. This is the total. Then the ratio, it had to show up as one of these for every 2 of those. So this is the total may be this, but each one contributes 1/3 here and 2/3 there because they're 2 to 1. 2 to 1. That's how I get these values. And now all we have to do is plug those values in here. Right? Put this one in here. Put this one in here. So I'm going to square that one, it's already in my calculator. And then I'm going to flip and multiply it by this. So I get 2.70. It's K P. Here. Okay. Did I lose anybody? Let's see, one more. 36. Oops, too far. There we go, 36. Certain temperature K for the reaction. I'm going back the other direction now. 2NO2 yields N2O4 is 7.5 liters per mole. These are both gases. Okay, so K equals 7.5, which is equal to what? N2O4 divided by NO2 squared. If 2 moles of NO2 are placed in a 2-liter container, initial, 2 moles of NO2 in a 2-liter container means 1 molar. 2 divided by 2. What's the concentration of N2O4 at equilibrium? Okay, we're starting off at 0 there. Okay, we're going to create some of this, right? It's going that direction because there's none of that. And we're going to lose 2 of these, right? All right. This also says that it's very far to the right, N2O4. So this is going to be 1 minus 2x, and this is going to be x. And if we plug those values in here, N2O4 is x divided by 1 minus 2x squared. Now, with a value like that, is x significant? Yes, x is very large compared to 1. So we cannot throw that one away. We're going to have to use the quadratic, unfortunately. So what do we got? We got 7.5 equals x divided by what? Can you expand the quadratic? 1 times 1. 2x times 2x is 4x squared. And then we add these 2 together. 2 of those, 2 of those. 2 times 1 and 2 times 1 is, let's see, it'll be like this. Be sure I'm doing it right. So 1, that one. And then this one times that one, and this one times that one added together, which is minus 4x. Okay? So that's how I got to that point. All right, now if we bring those over here, then that's 7.5 minus, let's see, 30x, right? 4 of these, 2 of those would be 15, and 2 15s would be 30. So that's this one. And then this one will be another plus 30x squared equals x. So now when you solve the quadratic, everything has to be on one side and 0 on the other, correct? So this minus x has to come over here. I mean, this x becomes a minus x. 7.5 minus 31x plus 30x squared equals 0. Now, this is for our quadratic equation. This is A, this is B, and this is C. Okay, so let's look at the question again. Calculate the concentration of N2O4. N2O4. So if we find X, that's our answer. All right, so let's do our quadratic. I can remember what it is. I think I put it in useful information. Yeah, there it is. So in this case, X is equal to minus B. So minus 31 is plus 31, plus or minus square root of B squared. So minus 31 squared minus 4 times A, 7.5. C, yeah, C, 30. Okay, all divided by 2 times A, which is 7.5. Okay. So notice we have a plus or minus here, so we're going to have two answers. What's the first one? Well, let's do this calculation in here. 31 squared is 961, and then 30 times 7.5 times 4. Rookie error. You see what I did? A is the coefficient of x squared. B is the coefficient of x. And C is the constant. Okay, I'm not gonna torture you with another quadratic. Once you solve those two, you should end up with, let's see, for comparison, 0.647 or 0.386. 0.687, 0.386. Those are our choices. X is equal to this one or that one. So if we look at question again, calculate the concentration of N2O4. So N2O4, the value for N2O4 would have been, let's see, where is it? X, okay, X. And the value of NO2 is 1 minus 2X. That's 1 minus 2X. This is X at equilibrium. Okay. All right, to evaluate this, you look at this original, which was 2 moles per liter, this is 1 molar. All right, so if we put this one in here, it's like 7, close to 8.2. Okay, that's a positive number. If we put this one in here, 2 times that would be 1.3 or 4, makes a negative number. Can't be negative. Right. So this one is out. That's the answer, 386. Or 3.39. Okay. If I had done that right, this would have been a better video. That's what I get for writing my equation backwards. Okay, I think that's it. That's enough. Now, we use quadratic. There's another approach that will work. And I don't know if I showed you that one in class. The method of successive approximations. Did I show you that one? Okay. What you do is, actually, I don't think this one will work very well for successive approximations because the K is too large. Successive approximations works pretty well for very small Ks. The large Ks tend to take you in the wrong direction. The overall successive approximations is you make that judgment call where you eliminate the X that's in the way. It's going to make you a quadratic, get rid of it. Do the calculation, find out what X is. And then you take X and you plug X into the value that you eliminated and keep the other X and solve for that X. And it should get closer to the answer. Then you run your 5% goodness value. See if it's close. If it's not, then you do the successive approximation again. You keep doing that and you gradually narrow it in. With our computers now, you can do successive approximations. You can build a program that'll do that for you. We used to do it by hand, which was okay. In this case, quadratic is better. If you end up with something like a cubic or a quartic problem to solve, successive approximations is the way to go. I know there's a cubic solution, and it's a mess. It's a formula of that. And I can only imagine that the quartic would be worse, like several orders of magnitude worse. Okay. So, any questions? So, what did I eat this morning, or what did I drink? Caused so many mistakes.
Monday.
It's a Monday, yeah. Okay, so let's see, this is next Monday, we'll have an exam on this material. And the midterm grades are due by close of business that day. So I should have time to get that grade in for you, as well as the corrections you've made.